Like, come on. Come on. All right, so today we're going to finish the mechanics or direct formulations. We're going to... Morning. I haven't decided what to do. Are you like at work? Are you coming from home? Like, how can we help you make this happen?
It's only 2 minutes.
Yeah, but it's like 2 minutes, man. Are you this late to Hicks?
I don't have really a start time yet.
Oh, God, I should have known that.
It's kind of whenever you...
Whenever you get there?
Yeah.
I'm going to tell Tom that you're screwing me over with that sort of system. So we're going to finish the direct formulations, all right? And then Monday, you have homework due. Monday, I'm going to give another homework. We're going to analyze. You're going to create a series of functions in MATLAB, okay?
So like guidance on how to do that?
Yeah, so
Okay, 'cause
His Holiness Mike Berry is going to be in here, okay, on Monday, all right? Try not to make his head any bigger than it already is, all right? And he's going to explain, or kind of, this class is really tough, I found, because you all are at different levels,
So that's
right?
why you have to teach it to us.
What's that?
You
Yeah,
have
yeah.
to teach it to us, not just tell us to do it.
Yeah, so that's where Mike is going to come in, because I have to give him credit, okay? Because he's in academia, right? In the real world, I never use MATLAB, okay? Never, all right? But in an effort to understand the theory of what's going on in the finite element method, we have to do some of that, okay? You could do it in Maple, but MATLAB's powerful because, like, from an actual, like, numerical valued approach, right? It has a lot of strong tools, but you can also do symbolic stuff too, and he's going to talk about that as well. But essentially, you'll just create, some of you, raise your hand if you've done some MATLAB.
Well, we all have it in
Okay.
one class, but it's.
Not all of you. Mike, have you?
Well, yeah, the same class.
It's one class where we did like 2 little short labs and that was it.
It's like a freshman year class.
Yeah, so it's been.
Oh, really?
4 years
Yeah.
ago. That's where like.
I was going to say, yeah, that's where I was
You
thinking.
don't do it in dynamics.
Yes, you do. You make a whole code instruction.
Regulars?
No, structural. But I haven't taken structural.
Yeah, yeah.
lab since freshman.
And you haven't taken it.
Yeah.
See, this is where the problem comes in. So,
Just post a code.
post the code, that's what I should do. All right, deal. Man, it's really easy over at Hicks, isn't it? They just like give you everything. Yeah. No, you're going to write your own, and you're going to write your own to essentially analyze a very simple truss, Aaron.
We have previously written a MATLAB code for a very simple truss. Can we use it?
In what class did you previously write a very simple code for a simple truss?
FEA.
Really?
Yeah.
What did the truss look like?
I mean, it was for any configuration.
Well, it's actually like a
truss.
money code, like far too complicated for me to understand, but like, so you can put anything in there. It's actually like really good, but he walks us through kind of how.
So he gave it to you.
You ever seen a
Yeah.
power line thing? We call it-
A power line thing? I've
Yeah,
seen
you know,
lots
the
of power
transformer
line
Big
things.
truss.
Yeah, the big truss.
Yeah.
That is, that, we did it with that.
But you didn't do shit. All you did is watch McGee walk you through.
No, he walked us through.
Yes,
in
he walked us
class,
through.
And then he's like, you gotta update it to make it for any problem. So we updated it.
Okay. It's going to be very specific. You can use that code, I think, to your advantage potentially, in seeing how the code's laid out and what it does. But I am looking for this in particular truss, right? It doesn't, I mean, it could be open for additional trusses, right? You could make it for more complex stuff. But I really am doing it in an effort to get you to understand kind of the processes and the steps involved of, right, figuring out your stiffness matrix. Then you need to figure out going from local coordinates to global coordinates. Then from global coordinates, you got to figure out, okay, well, you got to impose boundary conditions. Well, how do you do that? So your submittal, your deliverable to me is going to be your MATLAB code with some explanations of what's going on. So Elias, you cannot use that code because you don't know what's going on with it, right?
Right.
There's these portions of it that I have.
It's blackout, right?
Well,
It's
Mike's
just like,
code
oh,
is
it's
like,
cool.
like hitting it with a big sledgehammer,
Yeah.
and Ladine's is like kind of taking it apart with a nice precision
Scalpel.
tool. Yeah.
Yeah.
And then I don't get quite some of the little stuff.
I'm a brute force ad hoc kind of code programmer
Yeah.
too, which is fine, and that's fine for this homework assignment too that I'll give on Monday. But the effort of going through this, I think, is very valuable in the sense that you're understanding really what's going on within any finite element program, right? They've got to establish a stiffness matrix. They've got to calculate, or they have to impose boundary conditions. They have to understand what are applied forces versus reactions. How do we calculate what those are, right? How do we go from, right, VA, for instance, we've got all of these beam elements, right? To date, we've only really done like a series of all of these beam elements in one line down one coordinate, right? We can't do that in the real world. Everything's all off in space. So how do we do that? How do we apply that? So that's what we will do. So Mike is going to come in on Monday.
Can we start making like the homeworks due on Wednesday and not Mondays? Yeah. I just don't like Monday due dates.
None of you guys like Monday due dates?
Terrible.
Okay, don't
I
like
like to get
it.
it done with Friday.
I mean, it is Super Bowl Sunday next
Yeah,
Sunday.
I'm not gonna be wanting to do homework Sunday.
Really?
Not this Sunday.
And this is the weekend.
Oh,
so
the
fun
13th?
things.
Yeah.
13th is Super Bowl, yeah.
Wow. Sure. Why not? So I'll give it on Monday. It'll be due the Wednesday. So I'm gone the following week. All right. So I was gonna do some online lectures. I'll post them to YouTube. We'll be in energy methods at that point, which I'm assuming you guys will hopefully grasp some of that without me here. But we're gonna walk through some of that. So Monday we'll talk about MATLAB and kind of go through some. In structural dynamics, Mike handed out like a little note sheet, right? That kind of broke down some of the for loops and how
Oh, yeah.
the programming works and stuff. So we'll go through that a bit more. We're going to talk about plotting, talk about how you would do symbolic manipulations in MATLAB. Like how do you take the, A plus B, right? Where normally MATLAB, you have to define what A is and B is numerically before it would do A plus B, right? It's very simple. You just essentially say that A is a symbol instead. What's that?
Daniel was teaching me how to do that yesterday.
Yeah. I mean, it's very simple, right? Applying it. So, yes, Jan.
With that, since we're learning MATLAB Monday, is this upcoming homework due Wednesday? Yes?
Wow, you just,
What? I don't know how to do
man,
MATLAB.
you
We're
really
supposed
know how
do
to
it on the
squeeze an
homework.
orange, don't you?
What is Maple?
Maple?
I'm also curious about that.
Maple's essentially MATLAB, but it's more from a symbolic analysis perspective. So like you're using, instead of saying A equals 3, you just use A and you analyze it. It's essentially the same sort of software package, but it's based more on a symbolic representation than a numerical representation like MATLAB is. What's that? Anything else? So homework due Wednesday, all right. From now on, I guess it's due Wednesday. We'll go through MATLAB on Monday. What else? There was something else I wanted to ask you guys. Maybe we'll do it after this. You'll remember it.
It snows on Monday and Mike isn't here.
See, he told me that. He told me that. But honestly, looking at the weather, I think we're good. I think we're good. That's a real thing. That was like his first comment. What time is class at? Well, if it snows.
Your focus right there. I didn't even get my first
Just
try.
like, dude, what the fuck? Priorities is right, man. Jesus. Okay. So mechanics and direct formulations, right? At the beginning of the class, we talked about the finite element method in its entirety. We stepped through what is this idea of interpolation functions, and now we're actually getting into the meat of how do we figure out the nodal values, because once we know the nodal values, then we're just interpolating between nodes based on the element that we're selecting. So we need to figure out stiffnesses, right, or this geometric or characteristic matrix. All right. We did this going through a couple different approaches. We had the equilibrium method, right, where we just did a series of free body diagrams, figuring out the internal stresses. We reformulated these series of equations to give us forces within our element based on nodal displacements into this characteristic form, right? KD equals F, where Aaron was real disappointed in the lowercase values, right? So K, little d equals little f, all right? And really, this equation, right, in its form, is essentially a linear spring. Right? As I mentioned, it's probably just in general thinking about structures as a series of springs is not a bad approach to consider as you guys move forward. There was a second approach, which is the vector approach, where you essentially impose a unit displacement for one of your degrees of freedom, and then calculate the forces in which, right, each of the columns in our stiffness matrix is a vector of forces that would impose a unit displacement, right, or a unit degree of freedom for the degree of freedom in question, right, U1, for instance, and then 0 everywhere else. So we went through a series of derivations of our individual element, and then we went through and talked about, okay, well now we have multiple elements, because in the real world we don't just have one single element. And we can use that same approach to do that. Alternatively, which is, I think, the easiest method to do this, would be to just say, okay, if we can derive our initial element stiffness matrices, right, we can use the process of assembly to essentially add these stiffness matrices up into a full structure stiffness matrix that is the degree of freedom by degree of freedom size. So in our case, we have 3 degrees of freedom for the entire global system. Then we have a 3x3 matrix. You would assemble them, right, adding them into the matrices based on their, right, degree of freedom. So our first element would be U1, U2, and our second element U2, U3. Then, as we know in the real world, right, everything isn't just aligned along one axis. Things are in all different kinds of axes, not only in 2 dimensions, which we talked about, but in 3 dimensions. So we got our bar element, right? We have a local coordinates and a common coordinate system. In this case, we call this the global coordinate system, right? You'll be using this in the homework, right? So what does this do? Well, in Cook, he describes this method of the relationship, of determining a relationship between the degree of freedom locally, which in our linear bar element, right, is the displacement along the length of the bar, into vectors in 2 dimensions, right? This common x and y, which would be a u displacement and a v displacement vertical, okay? And establishing this relationship between the 2 is essentially just a series of cosines and sines of the components of our displacements, right? With respect to not only our displacements, which is the left side there, and our forces, right? Because when we calculate, we're going to say in a second here, but we're going to calculate things on a global scale and then backtrack into the local world. So we need to add up, right, our global displacements being v and u. Each one of those v and u's has components that are along the length of our element, and we need to add those up. Same with forces, right? We're going to get global forces, and we're going to need to add up each of the components into our local forces. So if we look at this series of equations for our single bar element, right, knowing that our local displacement, right, u prime is our global or common displacements times cosine or sine, based on their contribution and their component in each direction. So if we threw that into matrix form, you'd essentially get to pull out those cosines and sines, and you would get what we would call this transformation matrix T.
Do you remember what the convention is for beta? Like, does it need to be, I remember it's like, it gets kind of weird where you measure it from the horizontal up, but then like when you have,
Well, we get to like snake it around.
right, it's like kind of weird.
Yeah.
It's always going from the element to our common axis, right? The common axis to our element. So like, for instance, here, it's positive.
And it's always like the nodes in ascending order, right? Like you go, if you have an element that's pointed like this, you go from node like 3 to 4. It's a
Yes,
angle.
yeah, along the length, whatever you would impose as the local displacements of that element.
Yeah.
Right, so the homework I'll give, maybe you guys hopefully haven't done it, is essentially taking an element like this and adding an element like that.
Right, but does it always go counterclockwise, or it's just from the horizontal to that?
From the horizontal to your element.
So is it a negative, so
It can be a
you
negative.
do you go negative?
Yes. Because I mean, if you work back, right, you could essentially take whatever element you have. Say you have imposed in your first element that sat like this, right, your global coordinate system, right? The second you add a second one, your global coordinate system can't change. So you're really trying to find the contribution of this new element's displacement going in this direction, as Aaron said, right?
You basically just put that global right at the last node that you just found, right? And then you
Yes,
measure
the
to
second one, the beginning of your
Yeah.
second element. And then you're figuring out, okay, if I'm going this way, right, beta is now going downward
Yeah.
instead of going upward.
And then, but then when it's going off like to the side into that like third quadrant of, I guess, the unicircle, I guess so it's just the nearest.
It's always going in the direction of the elements, right? So you're gonna essentially apply element 1, element 2, element 3, element 4. And as Aaron mentioned, you
Direction of
starting
those
at your
elements, yeah.
first node of your element and traveling to your second node.
Yeah,
And so if you impose this global degree, global coordinate system at that first node, what is the angle from that global coordinate system to your local coordinate system for each of those elements as you travel?
gotcha, yeah. The local being in line with the element.
Yes, local is in line with the element.
Right.
For, well,
For
for
the
a
local.
linear line element like this, it's along the axis,
Yeah,
right? But if you had a series of beam elements that had displacements and rotations, right? Those coordinates, you're gonna have more than just this one local coordinate here. But the transformations are very similar. But we're not gonna get into them because it's muddies the water. Okay. So, essentially, to go from our global or common, right, little d, to little d prime, we'd essentially take this transformation matrix times our little d, or our global coordinates, right? Now we've got 2, because for a single degree of freedom, right, along the axis of the element, it's going to have 2 components, right, our x and y coordinates. So we have v1 and u1, right, and u2 and v2. So if we look at our forces, same thing, right? They have sine and cosine components that take our local forces, right, the force that's along the axis of our member, and creates an x and y component from it. We get this transformation matrix here, which is really the transpose of our displacement matrix, right? So we just flip it on side. If we multiply that by our local forces, we would get our global forces. Okay. So if we start with our local equation, right, as I mentioned, we're going to try and, we start at the local level, we're going to build up to the global level, and then we got to run back down to the local level, right? Because we're going to figure out what our nodal values with respect to our local coordinates are, because then we have shape functions, right, interpolation functions of our field variable that we know based on those local nodal values that we would then use and figure out. So we've got, right, our characteristic matrix, or our stiffness matrix in the local sense, right? K prime, D prime, F prime. Well, if we impose upon this now, knowing that our local deformation, right, U1 prime and U2 prime are equal to the transformation matrix times the global matrix of deformations, U1, V1, U2, V2. So we get this D prime equals transformation times our global deformation matrix. Well, that means that now we have K prime TD equals F prime. Well, we have this relationship that if we want to go to the global level, right? We can multiply the local forces times our our transposed transformation matrix. So we just multiply both sides by T transpose. When we do that, we end up with this big equation here. T transpose K prime T D F, whoops. Order of operations is important. T prime, F prime, right? So we effectively get our global, right? This we would say is our global stiffness matrix, characteristic matrix. So we get our common formula of KDF, right? Where K now, as mentioned above, is our T transpose local stiffness times T.
Are these capital Ks or lowercase Ks? Does it matter?
Doesn't matter, Amanda. I mean, I guess I could. What's that? No, you can't keep saying nothing. What the fuck?
That's what I told you, it's confusing.
I mean, I guess if you wanted to, you could do little k as for like your local sense, and then big K as your big sense. But like, a K is a K. I mean, I'm writing all capitals because Aaliyah says that I write like shit. So I couldn't really, this is a little K. Take that as a little K. And this is a big K. Okay.
K prime is
Know that.
okay, kinda.
Yeah, K prime's little K.
Actually makes sense, sometimes it gets meddled, because usually they use the capital lowercase distinction.
Yeah.
It can be a little confusing.
Well, I'm not usual, Elias, all right? Oh, that's what I was going to talk to you about this class after this, okay? Everyone, not just you, Elias. You have problems, man. They kick you out. Can I do that? Do you know if I can do that?
Yeah, you might have to get like you have to have a reason.
Just write them up? Maybe they're late like 4 or 5 times?
Just gonna rip his mask off.
Yeah. Okay. So yeah, lowercase, uppercase doesn't matter. What does matter is that when we do this transformation, so the transformation is done before we do the assembly process. So what does that mean? Well, that means when we calculate this global, right, this is big K, when we calculate big K, we're doing it for each of the contributing factors for each of our elements, right? This isn't the entire big K. So we're gonna say T transpose little k, or the local K for our individual element, times the transformation matrix, right? And that'll give you essentially the first. See if we can go back to it. Right, that's going to give you these 2 values, or these 4 values, right? But then you would get another contribution for the second element in the global sense, and you would assemble all of those. So this our T matrix, as you guys probably seen, right, is very, very simple. Things get very, very complicated as you go from local coordinates to global coordinates, that maybe you're going from, Cartesian to radial coordinates or something like that, right? Things get crazy. Well, there's people out there that have already developed these transformation matrices, okay? I'm not going to impose upon you guys the idea of having to figure those out, but just know that there's other ones out there, right? This one just works for our local to global in the 2D sense, right? So our transformation is for 2D rotation of a bar. And know that other ones do exist. but we just have different T matrices to make those transformations.
Have the same what?
Oh, shit. What did I say?
Have the same distance.
You're not supposed to be reading this. Have the same form. Right? Make sure we're consistent here. Thank you, Amanda. Glad someone's reading this. I thought you're all out there faking writing this stuff down. All right, so let's look back. Step back for a second, right? If we review our bar element, we've got local stiffness forces and displacements, right? And based on equilibrium and Hooke's law, we established this stiffness matrix, which looks something like this, right? We had U1, U2, we had F1 and F2. This was our KDF sort of relationship, right? Stiffness.
Those look like capital X to me.
Those are capital Fs, right? Because that came out of my little diagram there, all right? And you guys are hard to please. I kind of like the sophomores better. They don't say shit the entire period. I just talk away.
Your first
Right away.
comment was that you wanted more engagement.
I did, but now I'm like, now I'm going back, dude. Now I'm going back. Yeah, I like it when you guys don't say anything, okay? That's tough. All right. Then we make this transformation, right? We're going to do this for each of the elements. We know that our local transformation of displacement and our local transformation of our forces. And that transformation matrix is a series of cosines and sines. Get back here, cosine, sine. And making those transformations, we get the contribution in the global coordinate system of our stiffness of our local element, so that we can get this relationship between stiffness, displacements, and forces. Then, as I mentioned, you take these, right, and you assemble them in a global stiffness matrix, which has an extent of our degrees of freedom by degrees of freedom, right? So if we had 6 elements, right, we would have 5 degrees of freedom, right? We would then have a 5 by 5 matrix, okay? Or sorry, 4 elements. So add, right, our transformed stiffness matrix to an empty one. Skipping letters. Right, an empty, global, just keep blowing right by words here. I want to get out of here, you guys are engaging too much. Right, so what does that mean? Well, that means that, right, for every degree of freedom in our element, there's 2 global degrees of freedom. So our global stiffness matrix is a lot bigger than, say, the stiffness matrix that we assembled before with local coordinates, right? It's no longer just U1, U2, U3 by U1, U2, U3. It's U1, V1, U2, V2, U2, U3, V3, right? So a 3 by 3 becomes a 6 by 6. So if we pull back even further and figure out, okay, well, where is this process sitting in the finite element process? Well, we originally, right, the steps are to split up a problem into regions. Connected by nodes. What was that process called? Anybody remember? What? Discretization, yeah. Assembly, wow. Yeah, sure. Right, this is the beginning, right? We split up our problem into regions. We solve for nodal values. And then when we have nodal values, what do we do with them?
Put them back into the global.
Just overall in the finite element approach, right? Splitting up our model. What's that? Interpolate. Yep, exactly. Interpolate between nodes. When we think about discretizing, right, for beams and straight bars, it's a little bit different because a lot of times, right, in visual analysis, for instance, right, or RAM or RISA, when you draw a beam, you don't draw like a series of 10 beams, right? You draw one beam from node to node, and that's because a lot of times the interpolation function can represent the actual displacement between two nodes. And so there's no sense in over discretizing it, right? Separating it into more elements, right? Because you're gonna get the same answer. So sometimes it would just be common to just, like when we model beams, we just go from like joint to joint, right? You're gonna model the system, the cover over here on the HVAC system. We're not going to model like each one of those beams as 10 beams that run from end to end, right? It's just one beam from end to end. Refinement is not as critical with these elements. And it's these matrix formulations that allow us to figure out nodal values. So as part of the solution process for our nodal values, okay, here we go, Aaron. Was that you that blurted out earlier? First step, calculate element stiffness. All right. Transform our local stiffness to our global stiffness. Local to global. And we're going to make our way through the assembly of our structural stiffness, right, which is now in our global coordinates. So in our case, right, for this linear bar element, we're going to add degrees of freedom because now in the global or common coordinate system, we can go up and sideways, not just along the axes. So we're going to have this structure stiffness, right, K. We're going to have global displacements. Oh man, there's your uppercase. And then you would have a load vector F. Okay. When we assemble the load vector, right, we have forces applied directly to the nodes. Any ideas of some of the other forces we might have? Huh?
Moments?
Yeah, potentially, but where are those forces applied? Like where would a moment or additional forces, yeah, between nodes, right? Because the element has no idea what's going on between it. And so we got to take those forces that are acting on it and impose those forces on the nodes itself, right? So forces applied by elements to the nodes. Right, when you did the homework assignment and you had your column, right? Feel like I got 15, well, a lot of different answers, right? Some of you decided to put just the point load there. Some of you decided to distribute it at the nodes. Some of you decided to put a uniform distributed load on top of the column, okay? But when you did that for the plate has no idea that that load is imposed, right? So inside VA, it essentially does energy equivalent loads where it takes that uniform load and says, okay, that uniform load on the side is imposing this much energy, when we talk about energy methods, onto the actual nodes, and then it imposes those loads on the nodes, right? So if we were to look at this truss, right, we have 4 nodes, right? We have bar elements at each one of those 5 elements there, right? And we have this imposed load P4 in the Y direction. We essentially would have, right, U1, V1, U2, V2, U3, V3, U4, V4. Where would that P land in there? What's that? If you were developing a vector of forces there, right? And each one of those components related to a direction of those forces, right? Where would P land? P is on the 4th node in the Y direction. So it'd be V4, right? And it's in the negative direction. And we would have 0 forces in the other direction. Okay. As of right now, this is as we assemble the load vector. Right? These are the things we know. We also know that there's got to be forces at 1 and 3, right? Because we have supports there. But as we're developing this, right, that's where we end up getting to boundary conditions, right? Up to this point, we've only considered the structure stiffness and the applied loads, right? Things that we know. We have not considered the way the structure is supported. So if we looked at that little truss model, right, we know that U1, V1, U3, V3 are all 0, right? Those are our boundary conditions. Well, this load vector doesn't take into consideration that, right? These are known applied loads. Our stiffness matrix doesn't take that into account either, right? So we end up with this U1, V1, U3, V3 equal to 0. So we want to solve for displacements first. We know that displacements, global displacements equals, by just rearranging our initial equation, right? Displacement, stiffness times displacement equals force. Well, if we take the inverse, pull it to the other side, we can figure out what our displacements are. right? This is where our boundary conditions are. In our displacements. And without our boundary conditions, our stiffness matrix becomes singular. It's essentially, the determinant is 0. When you take the inverse of a matrix, you divide by the determinant, right? Well, if that's the case, we can't calculate the inverse. So what does that mean? Well, therefore, we need to have a method to incorporate those boundary conditions in our solution. So we can take the inverse, figure out what our displacements are, then come back and figure out what our forces are. One method is to partition and then solve. We partition our, whoa, that just jumped up, didn't it? KDF, right? We essentially partition by pulling out, right, or finding the subset of equations for which the displacements are unknown, right, and the forces are known. Then we solve for unknown displacements. And this only works as long as our elements are properly supported, which means we don't have rigid body modes. Actually, the thing can't travel off in space, right? It has to be sufficiently supported. And once we know those displacements, equations can be solved for unknown forces. These are our reactions.
Modes? Is that rigid body modes or nodes?
Modes. How dare you speak up? And in Cook's book, in 2.7, which we're going to go through in more detail now, it seems like on Monday, but we're going to go through that a little bit with respect to what does it mean by partitioning? What does it mean by imposing our boundary conditions? How does that change our stiffness matrix so that we can figure out displacements? And then from those displacements, we can plug everything back into the original equation, right, KDF, and figure out our forces based on those known displacements, which those displacements come from equations that are known. Another method, which is outlined in Cook a little bit, is we superimpose stiff springs. I'm going to say, or what would I say? It'd be like, or we manipulate, whoops. Our stiffness matrix to include those boundary conditions. And we use a couple methods, right? In the programming world, right? A lot of times this method is predominantly used for very complex problems, right? So these stiffness matrices get very large. And so essentially going through, imposing your boundary conditions, pulling out all of your equations where you have known values, and then calculating what those known displacements are, then plugging them back into the big overall equation, then figuring out your forces is time consuming. Okay, so what we end up doing is we manipulate the stiffness matrix from the beginning, so we don't have to pull those equations out. Okay, so we're doing it in our overall development of our global stiffness matrix so that it speeds up that process, because from a programming standpoint, whoops, 2M's or 1M in programming? 2? I feel like I got a 1 out there too. Partition method is bulky.
But there's no case in which you have to use the spring, like, you could always partition, it just
Yes.
possibly isn't always the best way to do it.
Correct.
Okay.
I mean by hand, but for very simple systems, right? It's a lot easier to do that than figuring out all the inverse and determinants of matrices and doing all the longhand math. But when you start looking at very complex problems with lots of computational like power behind it, it becomes bulky to like pull all that stuff out, solve it, and then put it all back in. And that process of coming out and going back in becomes bulky, and it slows the whole process down. And so there's a few different methods to do it. I'm still not 100%, I'm gonna be honest with you, about this infinitely stiff spring concept, okay? Because I know there's a method to do it. The method that I have always used is essentially zeroing out degrees of freedom with respect to known boundary conditions, right? And imposing unity everywhere that you're imposing like your actual degree of freedom, right? So you get this almost the identity matrix for degrees of freedom with which you have boundary conditions. But in concept, if you think about it, right, if you had a support, right, that support is essentially infinitely stiff because it's not allowing your node to move anywhere. And so just by saying that you have infinite stiffness is essentially forcing the displacement to 0 because it's not going to move at all regardless of how much force is on it, right? But what ends up happening, and I've been doing the homework that I'm assigning to you guys, is that I've been trying that method, and honestly, I've just had a hard time getting it to work out correctly. So we're going to go through both those methods on Monday, and then Mike will talk about how to implement some of that stuff. But in concept, right, I mean, it makes sense that you would just essentially take your original stiffness matrix, and then where you have degrees of freedom that you're imposing, say, a support condition where the displacement is 0, you could effectively make that really, really stiff. And that would force that displacement to 0. But you get some weird singularities and inability to invert your stiffness matrix, because ultimately that's what you're trying to do, right? Figure out displacements, is inverting it. So you end up taking the determinant, which is multiplying, the crosses, doing all of that stuff. And it gets really funky when you go infinite. And so you might be able to use a very, very large number instead. But I'm trying to confirm that. Make sense? Black magic, dude. Black magic.
Yeah, you lost me about a slide and a half ago, but that's okay.
Whoa! That's why I record these lectures.